For illustrating dielectric barrier discharge characterization using E-field assessment, we use an experimental setup composed of two E-field probes with their holders, a test tube filled with pure water and embedding a tapered electrode. The electrode is connected to a 50 Hz AC high voltage source. The voltage delivered by the source can be adjusted from 0 to 25 kV. Below the test tube, a Petri dish filled with pure water is placed on a ground plane and two E-field probes are used in order to measure both radial and longitudinal E-field components. In the first experiment, we measure the radial E-field component into the space between the test tube and Petri dish. At low voltage, the E-field strength increases linearly with the applied voltage and, once a certain threshold is passed, some DBD appear simultaneously with a dramatic increase of the radial E-field strength. At low voltage, the RMS value of the radial E-field displayed on the inset varies linearly with the applied voltage and its phase remains almost constant. Once the threshold is passed, the phase of the radial E-field is suddenly shifted by approximately 90 degrees and very fast transients appear on the signal. With increasing voltage, transients appear more and more earlier. On that curve we see that DBD appearance threshold is between 16 and 17 kV. In this second experiment, we are using a second probe to get the radial E-field component at the electrode level. At low voltage, the radial E-field strength is much stronger in position 2 as compared to position 1. Above DBD appearance threshold, the situation is the opposite. Contrary to what observed at position 1, the radial E-field strength at position 2 remains proportional to the applied voltage and is not affected by crossing the DBD appearance threshold, whether in terms of magnitude or phase. In the last experiment, two probes are used to measure both radial and longitudinal E-field components into the space between test tube and Petri dish. Below DBD appearance threshold, the polarization of the E-field is elliptical and is dramatically modified when crossing the threshold. Looking closer to the behavior of E-field polarization state versus applied voltage leads to identification of three different regimes: below 16 kV, for 17 and above 18 kV. The typical polarization states corresponding to these three regimes are displayed here, with the linear regime below 16 kV, the full DBD regime above 18 kV, and a transitional regime between them. Both linear and full DBD regimes can be explained using a simple model of the experimental setup, which behavior corresponds to a RC equivalent electrical circuit below 16 kV and RR equivalent electrical circuit above 18 kV. Finally, three nice pictures involving sub-millimeter spatial resolution E-field probes are given to illustrate the current case study on DBD.